imagine they're just sitting in the closet.
Yeah, exactly. But they're like a pair of used skis, so they didn't shell out too much for them.
Yeah, well, that's good. Hopefully we'll get some snow, you can use them. I don't know.
Yeah.
Okay, it's time, so I'm going to begin. So I should be sharing my screen, which you should be able to see.
Yep, we can see your screen.
So I had a bit of a discussion about who Ross McKinnon was last time. I won't do that again. So what I want to do over the next little while is try to address why the voltage of a lithium-ion cell changes with the state of charge, okay? And develop some simple physical models to understand why that happens. So I'm going to be using my document camera quite a bit. And since I wrote out the notes that I'm going to use and sent them all to you, I'm going to point to those notes as I speak about them. I don't normally do things like this. I usually write things down, but I don't know how easy it is to follow along on the document camera anyway. So we'll see how it works, and you can stop me and ask questions however often you want. So I'll be switching back between the PowerPoint and the document camera just to keep track of what I'm doing, okay? So I'm going to the document camera now. Okay, I think you should see the document camera now, is that correct?
Yep.
Okay, so the whole point is of what we're doing over the next probably 3 lectures is to try to understand why the voltage versus composition curve or state of charge. So if you're 100% charged and you go down to 0, the voltage of a lithium-ion cell changes. Might be smoothly varying. It might have a situation like this, with a step. All kinds of different behaviors happen. And why is that the case? So that's what we're going to work on. So we have to start simple. And the first thing we're going to do is take a look at what happens at the 2 electrodes in a cell. So you have a cell with a lithium metal negative and say a titanium sulfide positive. And when you connect these 2 things by a wire and you have an electrolyte with lithium ions in it, lithium atoms dissociate into ions and electrons and they travel to the other side and intercalate. So at the negative electrode, which is the lithium, the half cell reaction is just lithium atoms dissociating into ions and electrons. And at the positive side, those ions and electrons come along. I forgot to put the plus TiS2 here. Plus TiS2. Those ions and electrons combine with the TiS2 to make lithium intercalated TiS2. So if you add up the negative and the positive half cell reactions, you get the overall reaction, which is just lithium, a certain amount of lithium plus TiS2 goes to lithium TiS2. So the reactions reverse during the charge. Okay, so that was the first page of what I wanted to cover on the PowerPoint. Oh, somebody's waiting in the lobby, it says. Can somebody let that person in?
Yes, I think.
All right, thanks. So then, what do we do next? Well, we want to develop some very simple things. First of all, if you have a cell reaction like this, and you want to know the voltage that occurs that the cell will develop, the voltage is equal to the change in free energy of the reaction. So comparing the reactants on the left to the products on the right, the voltage is minus delta G over the number of electrons transferred divided by the electron charge. That's if you want to work out your changes in free energy in electron volts per atom. It looks like this. But if you want to work out delta G in terms of joules per mole, which is more common in chemistry, then you have delta G in joules per mole, and you divide by the number of electrons involved in the reaction and divide by Faraday's number. Faraday's number is 96,500 coulombs per mole. So as an example reaction, one thing in the early days that was postulated for the lithium air cell was 2 lithiums plus half an oxygen goes to Li2O. Later, people learned that the reaction product was lithium peroxide and maybe even lithium superoxide. But anyway, if you think this is going on, you can look up the free energy of reaction for this reaction, and it's minus 580 kilojoules per mole. So to figure out the voltage of a cell that had lithium as the negative, carbon black exposed to the air, so oxygen, if we get to it, as the positive, and the product lithium oxide, it's just use this formula and you get 3 volts. And that's about what the voltage of a lithium air cell turns out to be. So, chemists like to work in joules per mole, and physicists like to work in EVs per atom. And if you ever want to convert between the two, this is how you do it. You have 1 EV per atom, 1.6 times 10 to the minus 19 joules per electron volt, times Avogadro's numbers atoms per mole, and that gives you 96,500 joules per mole. So 1 EV per atom is equivalent to 96,500 joules per mole. Okay, so that's a useful conversion factor. So I'm going to go back to my PowerPoint for a second. Stop me and ask me questions if you want. Okay, so I was supposed to tell you how to calculate cell voltage. I was supposed to use the lithium oxygen cell as a example, and I was supposed to work out useful conversion factors. So I did that. So intercalation systems aren't so simple. Their voltage varies with the amount of lithium filling the available sites. So the voltage varies, as you can see. There's not a fixed free energy change that takes place when you have a material that has, say, 0.2 lithium, and you add a little bit more. The free energy change is different than it is if you have a material that has 0.6 lithium and you add a little more. Voltage is different. Different materials show different behavior. So how do we treat the situation when the voltage varies with the state of charge? That's the question. So I'll show you how to do that and go back to the document camera. Okay, so I think you should be able to see the document camera. Is that true?
Yes.
Okay, good. And can you see to the top of the camera, or do I need to move it down?
You need to move it down.
How's that?
What we currently see is volts is equal to the negative gives free energy.
I think that's about good there, isn't it?
Yes.
Okay. So like I was saying, for lithium TiS2, the voltage is not constant, all right? And we have this formula for the voltage. It's the change in the free energy due to a change in the number of lithium moving from the negative to the positive. So delta G over delta N. So before we had delta G over N. But now we're just going to consider what happens when a small amount of lithium moves from the negative to the positive. So you can write the change in free energy that takes place due to a small change in the amount of lithium moving from the positive to the negative in terms of the derivative of the free energy of the positive electrode with respect to the amount of lithium in it minus the change in the negative electrode free energy with respect to the change of the amount of lithium in it. So this function G sub P is the free energy of the positive as a function of the number of lithium atoms in it. And G sub N is the free energy of this should be the negative. I don't know who wrote this. As a function of the amount of lithium in it. And these derivatives, dG, dN, are chemical potentials. So the free energy change is equal to the chemical potential of the positive minus the chemical potential of the negative, multiplied by the number of atoms you move from the negative to the positive. Okay, so that's very simple. And that means the voltage, which is minus delta G over delta N, which is this. Bring the delta N over here. You get the voltages minus the difference in chemical potentials divided by the electron charge. And if we use lithium metal as the negative, we define the chemical potential of lithium metal as 0. Okay, so if we're measuring relative to lithium metal, this is just minus mu P over E. And the reason that the chemical potential is useful is because it's something we can calculate from simple models of intercalation materials. And that's where we're going next. So I'm going to share my screen again just to see where I am. I think you should be able to see my screen now.
Yes.
Okay, so now it says lattice gas models are used to describe the potential versus composition curves of intercalation compounds. So it's very likely that many of you don't know what a lattice gas model is. So I need to define that for you. I'll talk about it for a minute first, okay? So we've talked about the structure of positive electrode materials. We've talked about the structure of graphite. We know, using, say, titanium sulfide as an example, or cobalt oxide as a example, that the host is made up of atoms bonded tightly together. For example, in titanium sulfide, there's sulfur, titanium, sulfur slabs. And in between those slabs, there's places that lithium can be put. And the lithium goes onto the octahedral sites. And those octahedral sites make a close packed layer, which is a two-dimensional triangular lattice, which I'll draw in a minute. Okay? And what we say is that if lithium metal on our scale is at 0 volts, its chemical potential is 0. When we take a lithium from lithium metal and we put it into, say, titanium disulfide, the lithium is bound. It has a binding energy of somewhere around 2 volts, negative 2 volts. It's bonded relative to lithium and lithium metal by about 2 volts. So we define something called the site energy, which is the energy difference between a lithium atom in lithium metal and a lithium atom occupying a site within the host. That's the site energy. So I'll go back to my notes and show you what I mean. I think you should be able to see my document camera again. Is that true?
Yes.
Okay, so can you see up to the top of it here, where my pencil tip is? Maybe you can now.
Yep.
Okay. Excuse me. So these squares represents the sites, close packed octahedral sites in the van der Waals space in titanium sulfide where lithium can be put, or the space between the cobalt dioxide slabs and lithium cobalt oxide where lithium can be put. And the fact that the square is empty means there's no lithium there. And if we add a lithium to a site, so we bring the lithium from lithium metal through the electrolyte, and the electron goes through the wire, and the lithium goes plunk into the site, it reduces its energy by E0 compared to a lithium atom in lithium metal. That's what we mean by the site energy. And then we define the fraction of sites filled, X, equals the number of sites that are filled. So here it's just one site, divided by the total number of sites. And here there's 10. So here X would be 0.1. And for this model, we can calculate the voltage curve at 0 Kelvin. So how do we do that? The free energy of the positive electrode is equal to the internal energy minus the temperature times the entropy. The temperature is 0 at T equals 0, so that term goes away. And the Gibbs free energy has a PV term. But if the applied pressure is very small, this is neglectable. So this V is volume, not voltage here. And what is the internal energy of this system? Well, it's just E0 times the number of filled sites. That's what it is. So the free energy of the positive electrode is minus E0 times N. So all we're doing here is we're totally neglecting the contribution of the host itself, because we say the host doesn't change. When we add the lithium, the host doesn't change in a material way. The bonding between titanium and sulfur doesn't change effectively very much. We just say, put the lithiums in, and they have this binding energy minus E naught. And then all you have to do is to calculate the voltage, it's the difference in the chemical potentials of the positive and the negative. You take the derivative of the positive free energy with respect to N, and you get E naught. I guess there's an E here, sorry. So the voltage curve is a straight line. Okay, fine. So this is a warm-up. This is a warm-up just showing us how to do the procedure. And now we're going to start worrying about what we do to get a sloping voltage curve. I'm going to share my screen again, just to make sure that I'm doing what I'm supposed to be doing. Right. So now we're going to talk about what happens to get a sloping voltage curve. So the first thing we have to consider is the fact that when we put two lithium atoms into these sites within the host, and if they're close together, they will interact with one another, because lithium, as you know, is a very good electron donor. So it will tend to donate its valence electron to the host and sit in the lattice as an ion or a screened ion. I'll talk about screening in a minute. But the point is, if you put a lithium atom close to one that's already there, you'll have to pay an energy cost due to the repulsion of these two positively charged species. Okay. And now we have to figure out how to deal with that. So that's what we're going to do. So we're going to go back to the document camera. You should be able to see the document camera again. Is that true?
Yep.
Okay, good. So let's make an estimate about how large the energy of interaction should be between two lithium ions placed on adjacent sites. So if you assume they're each charged with a single charge, so they're lithium plus, and they're about 3 angstroms apart, that's the typical spacing between adjacent sites in lithium cobalt oxide, NMC, NCA, spinel, everything. It's all about 3 angstroms. So what is the interaction energy between two lithium ions that are 3 angstroms apart? Well, this is something that you learned in first year physics. What is the potential energy of two charges placed a small different distance away? And it is calculated by saying, okay, you have one charge there, and then you bring the other one from infinity. How much work do you do to put it 3 angstroms away? And that's the potential energy of the configuration. And the answer is, it's Coulomb's constant times the charge of the first charge, the charge of the second, divided by the distance of separation. And that's in SI units, which would come out in joules. I don't like joules because they're not very useful to us. But anyway, we'll convert from joules to EV. So the Coulomb constant is 9 times 10 to the 9. The electron charge is 1.6 times 10 to the minus 19 coulombs. And 3 angstroms is 3 times 10 to the minus 10 meters. And then you convert from joules to EV. And you end up getting 5 electron volts. Okay, 5 electron volts. And that's just too big. It means that, okay, if you put the first lithium in, and that had a binding energy of 2 volts or something, if you put another one near it, it would be unbound. You couldn't put it there because it's only bound by 2 volts, and now you're asking for a 5-volt penalty. So you could never put a lithium atom in the near neighbor site. And we know from experiment that we can put lithium atoms in the near neighbor site in titanium sulfide and lithium cobalt oxide. So what's going on? What we're talking about here is called the Baer-Coulomb interaction. It means an ion with a 1+ charge and another ion with a 1+ charge. But we've forgotten something very important, and that's called screening. So if you put a lithium atom into something like titanium sulfide or lithium cobalt oxide, the lithium, as I say, is a good electron donor. It will tend to donate its valence electron to the host. But where does it go? The electron goes into the electronic band structure of the host. It can move around. But because there's a positive charge here, that positive charge will attract negative charge to it. And you'll get kind of a cloud. It's called a screening cloud of electrons around each positive charge. And depending on the density of free electrons in the material, if it's metallic, the screening will be good. You'll attract a lot of electrons around the positive charge. And you won't have to go very far away before, if you draw a circle around the positive and these enclosed electrons, that it looks neutral. So this is a big confusion for many people that talk about intercalation compounds. They say, oh, there's an ion intercalated at the site. And someone else will say, oh, no. Don't think of it as an ion, think of it as an atom. But really, you need to think of it as a screened ion. And the screening length, you know, how densely these electrons are around the positive charge, depends on the electron density in the material. So it's a screened ion that's in there, not a bare ion. And this screening reduces the interaction energy between the two ions placed nearby. So I don't know if you've talked about screening in other courses that you've taken. It may or may not be the case. But the point is that each ion attracts a screening cloud of mobile conduction electrons. If there are lots of electrons, like metals, the screening is good. And that means the interaction energy will be smaller than if the screening is poor. And this interaction energy between the two lithium atoms is normally much less than the Baer-Coulomb interaction. So, you know, we said it's 5 volts. It's normally much less than this. It might be 1/10 of it. So half a volt would be a typical, perhaps a typical number.
Hi, Jeff.
Yeah.
So yeah, we talk about the screening in the chemistry course, but I have a question here. So you mentioned for this screening effect, if the host is like metals, the screening effect will be more significant. But most of the cathode materials, they are not. I think they're not metals, right? They are semiconductors or they are not pure metallic. Does that mean like if a host materials, the more metallic characters they have, the better that's for lithium intercalation, because it provides more screening?
I don't think it necessarily means it will be better for lithium intercalation. It may mean the slope of the voltage curve might be a little bit less. We'll talk about 2 situations where we have good screening and poor screening later on, where one material we're talking about is a semi-metal and one is a metal. And we can see the difference in the voltage curve between the 2 of them.
Okay, thank you, Jeff.
Any other questions about this point before I go along?
Jeff,
Yeah.
so can we think of this as, you know, you have those electrons that are randomly spread out throughout your material. Some of them can be used to sort of charge balance your lithium ions, and then that's why you pretty much prevent any repulsive interactions, right? Because you have that charge balance from the screening electron, kind of.
Yeah, that's right. I mean, if you put a positive charge into a sea of negative charge, the positive charge will attract a screening cloud of negative around it. This is what you're saying. And once you go far enough away, the net charge inside will be 0. And outside of that radius, you just don't interact with this thing anymore at all. All right, so let's continue here. So what we have to do then is, as we fill up these sites with lithium, we're going to start filling up these sites. We know that any physical system always exists in the lowest possible free energy state. So that means if there's an interaction energy between these two that's positive, we will want to avoid putting lithiums on the near neighbor sites until the last possible minute when we can't possibly avoid it anymore. So if you were just filling sites like this, you would never put 2 of them side by side if this was the configuration you would start with. You'd fill, you know, one over here and one over there. So when we're trying to do the statistical physics of the lattice gas model and work out the free energy of the lattice gas, which is the arrangement of lithium atoms on the triangular lattice, we have to understand that G has to be a minimum, and we want the internal energy to be a minimum, which means we want the lithium atoms to arrange themselves to, you know, minimize these interactions as much as possible. And we also want the entropy to be a maximum, because G is U minus TS. Okay, but it's also plus PV, but I'm going to ignore the pressure volume term because it's very small. And we want to do these calculations at real temperatures because we don't exist at 0 Kelvin. Okay, so solving the lattice gas problem exactly is very difficult. You can't use analytical methods to solve the lattice gas model exactly, except in very special cases. So you can use computer methods like Monte Carlo simulations to do it, but that's beyond the scope of this class and way more sophisticated than necessary to understand in general terms what's going on in these lithium-ion cells. So what we do is we define, in addition to the site energy, which we've already talked about, we defined interaction energies. So a lithium atom interacts with another one in the next neighbor site with an energy called U1. That's called the near neighbor lithium interaction energy. And if you're talking about 2 lithiums that are separated on the next near neighbor pair of sites, we'll call that U2, the next near neighbor lithium-lithium interaction energy. And you could take the 3rd neighbor, which would be this one, and talk about U3 if you want, right? If you want to include more interaction energies, you can include U3. And some theoretical people, very famous, like Gerd Cedar, Anton van der Ven, and people like that, they also have another type of interaction that depends on a triangle. So 3 lithiums together creates another type of interaction energy. In addition to the 3 near neighbor ones you get, there's also a penalty you pay for having a triangle. So you can do whatever you want, but here we're just going to keep things really simple and just talk about U1 and U2. Okay, any questions about this? Okay, so I'm going to go on. So the simplest approximate solution to this problem is something that in McKinnon's thesis he calls mean field theory. And I encourage you to read that section of the thesis because it's much better than I can do here in the lecture. And what you do is you assume that the lithium atoms remain randomly distributed in the sites in spite of the interactions. Okay, so this is a very dramatic assumption, right? It's always going to favor entropy because the biggest entropy you can get is a random distribution. And you're just going to say, you know, I know there's an interaction, but I'm going to assume they're randomly distributed anyway. So that means if you look at any particular site, the probability of finding it filled is just equal to X. So I'll remind you what X is. It's the number of lithiums divided by the number of available sites. So if this is equal to 0.1, each site would have a 10% probability of being filled at any given time. So if you make this assumption, then you can write down the internal energy of this lattice gas by inspection, basically. So let's do that. So we have big N sites, and in this case there's just whatever it is, 11, 10, and some fraction X of them are filled. So the contribution to the internal energy from the binding energy is the total number of sites that are filled times E0. The total number of sites that are filled is little n, and that's big N times X. So we're going to factor out the n's here because it's going to be most convenient to do this later on. And then we have to worry about all the interactions that take place here, right? So what we do is we go to a particular site, say this one, and we ask, is it full? And what does it interact with? Well, it interacts with its neighbors with U1. It interacts with its next neighbors with U2. So if we look at site I and site J, we have to worry about the interaction between sites I and J. And as we go through this lattice, we start with this and examine all the other sites, look for their interactions. Then we move to the next site, examine all the other sites and the interactions. We'll count the interaction between these two sites again. So when we have this site as our focus site, we'll count that interaction. When we have this site as our focus site, we'll count that interaction again. So there's a factor of a half out in front here. And then if you say, okay, fine, I don't care about interactions out to the gazillionth neighbor, what happens to this term if we just focus on first and second neighbors? Well, then you go to a site, and this sum over the other sites, there's only 6 near neighbors in this triangular lattice. If you look at this one, you can see there's only 6 near neighbors. The probability that this site is full is X. And the probability that each of these other sites is filled is X. So you pay this interaction energy when both of them are filled. This is filled with a fraction possible probability X, and so is that. And there's 6 near neighbors. So this gamma 1 will be 6. U1 times x squared. The probability of each site being filled is x. This is 6 for the triangular lattice, and there's big N focus sites. As you do this sum, you have to go to every focus site, and again, there's a factor of half because you're at this focus site, you get that interaction, and when you're at that focus site, you get it again, and you don't want to double count, so that's where the half comes from. And it's the same argument for the next near neighbors, okay? So that's the internal energy just written down. And the entropy is also easy to write down because it's a random distribution. And the entropy is Boltzmann's constant times the logarithm, this is the natural log, of the number of ways of arranging the N lithium atoms on big N sites. And it doesn't matter if you've had statistical physics before or not. I'm just telling you what the number of ways of arranging N lithium on N sites is. It's N factorial over little n times big N minus little n factorial. And then you use Stirling's approximation for the logarithm of big N. And the entropy just simplifies down to this incredibly simple form. It depends on the fraction of filled sites. So this ln here is the natural log, and this log is also the natural log. I just tend to just go between the two ways of writing it without even thinking about the difference, so I'm sorry about that. So you have a simple expression for the internal energy, you have a simple expression for the entropy, and that means you can write the free energy of the lattice gas. So we'll do that. The free energy of the positive electrode is just U minus TS. I told you what U was, and I told you what S was. All right. And then the voltage is related to the negative, the chemical potential. But the chemical potential is just the derivative of the positive electrode free energy with respect to the number of lithiums that are on it. So that's GP by d big N times X, which is 1 over N dG dx. So this is really convenient. You can just differentiate this expression with respect to X, and you get the chemical potential, and you take minus mu over E to get the voltage. So if you do this differentiation, this is what you get, which is in the square box. So a really simple looking expression for voltage as a function of the composition. It depends on these interaction energies, it depends on the temperature, it depends on the binding energy of the lithium to the site. This factor KT over E at room temperature is 25 millivolts. So the entropy contribution to the voltage profile is on the scale of, you know, pretty small, 25 millivolts or so. You can also calculate the differential capacity. You take the derivative of the voltage with respect to X, and then you invert it. And I just have omitted all the calculations because really what you need is the result, which is here. Okay, so all of this has been sent to you by email, so you have all this stuff. And really what's important is what's coming now, which is what happens when you play around with this simple equation? What do you learn? So does anybody have any questions about these equations, where they come from, before I start talking about, you know, what happens when we play around with these equations? You know, and at the level of this class, the really thing that's important is the final result, not really how we got here. Although in some of the homeworks, you know, I will be asking you to think carefully about these interaction energies and so forth. Okay, I'll go back to my PowerPoint since I hear nothing.
Hey Jeff,
Yeah.
sorry, I do have a question. So the model you used, since the lattice for graphite or all other systems sort of have the same lattice structure, the only thing that's going to vary is the distance between or the lattice parameter, right? So under this model, they're all going to have the same voltage. The difference that the lattice parameter is going to change, or is there other things that change?
Go back to this. Okay, so they're all going to be different, and the reason is that this E0 is very different from one material to the next. Let's talk about it. So imagine you put lithium into graphite. Okay, that's going to be one thing we're going to talk about. And now imagine you put lithium into titanium sulfide. Think about sulfur. It's a really good electron acceptor. Think about lithium. It's a really good electron donor. Now think about graphite. Lithium's a good electron donor, but carbon's only a weak electron acceptor, right? It's not over to the far right of the periodic table. So which do you think has a bigger binding energy for lithium? Titanium sulfide or graphite?
Titanium sulfide.
Good for 1 tau. You win a prize. I'll put it on your desk after class.
Thanks.
Okay, so now let's talk about interaction energies. Let's talk about MO6Se8, where the lithium atoms are spaced by 8 angstroms, and it's a metal. And now let's talk about titanium sulfide, where the lithium atoms are spaced by 3 angstroms, and it's a semi-metal. Which do you think has the greater interaction energy, titanium sulfide or MO6Se8? The lithium atoms are 8 angstroms apart in MO6Se8. They're so far apart and they're in a metal, they hardly feel each other. In titanium sulfide, they're super close and they're not well screened. So the point is that from one material to the next, these parameters change. E0 and the U's change from material to material. So is that helpful?
Yeah, thanks.
Okay, cool. Okay, so we're almost out of time, but we're going to go back to the PowerPoint for a minute. Okay, so I did this, and I did that black slide. That's when I go to the board and write stuff down. And I wrote down the Gibbs free energy, and I wrote the chemical potential and the voltage. I wrote down the differential capacity, and now it's time to explore our model. So we'll just look at one slide here about our model. All right, so here we are. So I've set the value of E naught to be something like 2.2 volts or so. And this blue curve here shows you what the voltage versus composition curve would look like if there was no interactions at all. Okay, so all we have here is first neighbor interactions, and the blue curve is for no interactions at all. So the only thing that's happening is the entropy effect. So it's almost like what we calculated for the t equals 0 case, which was a straight line, except because of this entropy, there's a small slope, and at the ends, there's quite a steep steep slope happening at the ends that you can see there, okay? The black curve is what you get if the interaction gamma times U is equal to 1 electron volt. So if gamma is 6, that means the near neighbor interaction is 0.16 electron volts. And here you have a slope of basically 1 volt over the full range from x equals 0 to x equals 1. All right. So this is where the sloping voltage curve comes from in these intercalation systems. It comes about because there are repulsive interactions between the lithium atoms that are placed into the materials. And it makes sense that there should be. Now, there's another curve shown here, which is for attractive interactions. So if gamma U is negative, that gives you an attractive interaction. So the red curve is what you get if you have an attractive interaction. Okay, and you might be saying, wait a minute, hold it a minute. Wait a minute, man. Where does an attractive interaction come from? So does anyone have any idea where an attractive interaction might come from just before we stop?
It is because the wonderful interaction.
Nope.
Okay.
How about if you have a system where you can intercalate both anions and cations?
Well, I don't know if that's ever possible. But
like when we are putting lithium, when it comes close to oxygen, so is that, can we count that as an attractive interaction?
well, that would be a strong site energy, I would say. Like we want to find a case where there's 2 lithium atoms in the material that want to come close together, not stay far apart. For some reason, they decide we would prefer to be very close as opposed to being far apart.
Jeff, it is more like the covalent compound, which the lithium like change their ionic nature to like more covalent nature. So they form like covalent bond between 2 lithium atoms. Would that be possible?
No.
Okay.
Well, if lithium is reduced to lithium metal,
Well, you know, if the thing is virtually no charge, well, then I don't think it would really want to be next to each other. It would just sort of be happy wherever it is. Okay, so you folks can all think about that over the next days, and we'll talk more about it next time. I think we're out of time, right? I even went over time. Okay, so I went over time. I apologize for that, and we'll pick this back up again on Monday. Oh, I think you might have a homework due on Monday. Is that correct? I don't remember when it's due.
That's Wednesday.
Oh, it's due on Wednesday? Okay, fine. So you have lots of time. All right, I'll see you on whatever it is, Monday. Okay, bye.